We're back with part 4. We will answer the conceptual concept questions and we'll tackle solid states of matter. So we'll look into ionic solids, metallic solids, and covalent solids. What happens to the vapor pressure of a substance when its surface area is increased at constant temperature? The vapor pressure remains the same. B. And using this figure to estimate the boiling point of water at an external pressure of 200 torr. So you can see you want to go to water, 200 torr, and you're going to estimate it by kind of dragging that right down. And it's definitely not like 84 degrees. It would definitely be 66 because clearly not 100 and not 0. So the answer is A. When most liquids are cooled, they eventually freeze into crystalline solids. In a crystalline solid, the atoms, ions, or molecules are arranged in a regular repeating pattern. However, a liquid can sometimes freeze before its particles have time to organize into this orderly structure. When that happens, the solid form is called an amorphous solid. In amorphous solids, the particles are arranged randomly and do not have a repeating internal pattern. Metals and ionic compounds usually form crystalline solids because their particles pack together in an organized way. Substances made of large molecules or mixtures of molecules that cannot move easily are more likely to form amorphous solids. An example is candle wax. That's an amorphous solid because it's made of large hydrocarbon molecules. Some substances, such as silicon dioxide, can form either crystalline or amorphous solids depending on how they're made. Under the right conditions, amorphous solids can slowly change into crystalline solids. Crystalline solids are classified based on the type of forces holding their particles together. These forces strongly affect the solid's physical properties. The main types of crystalline solids are ionic metallic, covalent network, and molecular solids. Ionic solids such as sodium chloride and nickel oxide are made of positively charged ions and negatively charged ions held together by strong electrostatic interactions. These attractions are often very strong, which is why many ionic solids have high melting points. In ionic compounds, the forces between fully charged ions are much stronger than the attractions between partially charged ions found in polar molecules. This idea will be we'll go into a little bit more depth when we cover lattice energy towards the end of this part. Although ionic solids are hard, they're also brittle. So instead of bending when the force is applied, they'll crack or shatter. Ionic solids do not conduct electricity in the solid state because all the ions are locked in place. However, they can conduct electricity when melted or dissolved in water, since the ions are free to move. Many simple compounds formed from a reaction between a metal and a nonmetal are ionic in nature, so keep that in mind. Molecular solids have lattice sites that are occupied by molecules, so like carbon dioxide, water, glucose. The molecules are held together by those intermolecular attractive forces, like Lund dispersion, dipole-dipole, hydrogen bonds. They have weak attractive forces and relatively low melting points. And some crystallize in different structures, so they're called polymorphs, and they have different properties. In addition to ionic solids and molecular solids, there are atomic solids. Most notable are covalent network solids, which include crystals of diamonds, silicone, and some other nonmetals. And some covalent compounds, such as silicon dioxide, which is sand, and silicon carbide, which is like the abrasive stuff on sandpaper. Many minerals have networks of covalent bonds, and the atoms in these solids are held together by a network of covalent bonds. Who knew? You couldn't tell by that name, right? To break or to melt a covalent network solid, covalent bonds must be broken, and because covalent bonds are relatively strong, covalent network solids are typically characterized by hardness, strength, and high melting points. For example, a diamond is one of the hardest substances known and melts above 3,500 degrees C. Metallic solids such as copper, aluminum, and iron are made of metal ions arranged in a crystal structure. As you can see here, this is copper in a metal solid in the figure shown on the slide. These crystals are often described using a sea of electrons. So we learned about a sea of electrons in metallic bonding, right, in our first module. This is where positively charged metal nuclei are surrounded by a shared pool of delocalized or freely moving electrons. This type of attraction between the metal ions, like I just mentioned, is called metallic bonding. Metallic bonding gives metals many of their familiar properties. Metals conduct heat and electricity very well, have a shiny appearance, and are malleable, meaning that they can be hammered or shaped without breaking. They're also strong and hard, which makes them useful as construction materials since they bend rather than shatter under stress. And they have a wide range of melting points. For example, mercury is a liquid at room temperature. Alkali metals melt below 200 degrees C, and several post-transition metals also have relatively low melting points. In contrast, most transition metals melt at very high temperatures, often above 1,000 degrees C. And these differences are due to the variations in the strength of the metallic bonding among the different metals. Here's a lovely table to help you categorize in your brain about the different types of solids and the different types of particles that are within those solids, what type of attractions they have, their properties, and some examples. So you can use this for reference as you're doing homework or going through the end of the chapter problem, studying for the exam. In a crystalline solid, atoms, ions, or molecules are arranged in a regular repeating pattern. However, this pattern is not always perfect, and defects can occur. Several common types of defects exist. One defect is called a vacancy, and it occurs when an atom or ion that should be in the crystal structure is missing. In some cases, atoms or ions may squeeze into spaces between the regular positions in the crystal, and these extra positions are called the interstitial sites. Defects can also form when a crystal contains impurities. If the impurity particles are too large to fit into the normal position in the crystal, they can distort the structure. Sometimes small amounts of impurities are intentionally added to a crystal in a process called doping. Doping creates controlled defects that change the material's property in very useful ways, like silicon crystals are doped with small amounts of other elements to adjust their electrical behavior. This makes silicon useful for making semiconductors and computer chips. Who knew? Another little brief video ending with our favorite things, conceptual connection questions. This one asks, high pressure favors the formation of a diamond from graphite. What can you conclude about the relative densities of the two substances? So in order to answer this question, I would go to your book because we did not really dive into diamonds or graphites, but the book does have an explanation on them. So definitely pause here, flip, and kind of go through it. Your answers are A, diamond is denser than graphite, B, graphite is denser than diamond, or C, nothing can be determined about the relative densities of the two substances without more information. And next, which solid would you expect to have the highest melting point? Would it be magnesium oxide, iodine, or kryptonite? Tune into part 5 for the answers.